We're starting section 4.7 on applied optimization problems today. And if you click on the first link in the Friday resources for the week, you'll come to this page where I've got a river graphed right below the x-axis. And we are going to be building a pen today for our favorite goat. And we're building it up against the river so that we only have to build 3 sides of the pen, ostensibly because the goat's not going to jump into the river. And the pen has this drag me point on the right, so you can choose the size of your pen. But as you drag it around, you're going to notice that it's not going to let you choose just any size pen you want. And that's because I have programmed into this page a constraint that we only have 2,400 feet of fencing. So if I want to make the pen a little wider, it forces me to make it shorter. And if I want to make it taller, it forces me to make it a bit more narrow. And the question we're going to answer about this goat pen is, how big should we make it to maximize the area or the space that this goat has to roam around? So I have these labels here, and for different values of the height and width, and you can check at any spot that it's going to make those 3 sides of the pen add up to 2,400 feet, no matter where you drag it, then you get different values of area. So right now, when I make this 860 by 680, I get an area of 584,800 square feet. And when I drag it really wide, slightly bigger area, 587,387.5. And so we kind of could play around and guess, it looks like just over 700,000 square feet of area is the maximum area I can get out of this. But the question we want to answer in 4.7 is, how can we calculate this precisely? How can we find the maximum of something or the minimum of something by using calculus? And this is a really important question to answer. If you have a business, you're going to want to figure out how to maximize your profits or minimize the amount of materials that you're going to use to build something. All right, so I'm going to try to recreate our pen along the river here. I'm going to draw myself a little river and my pen. And we had H for the height and W for the width. We're making this a rectangle, so it's implicit that this side is the same length, H. And I said that our constraint on this problem is that we had 2,400 feet of fencing, and that our goal is to find the maximum possible area. All right, so this is going to rely on our skills of finding the absolute maximum of a function on an interval. So I need to find a function for area so that I can find its absolute maximum using our techniques from 4.3. All right, so let's talk about the area. Obviously, this is a rectangle, so my area is going to be length times width, or in this case, h times w. And I would want to find the absolute maximum of this. I'd want to take the derivative to find the critical points and test those endpoints, but we've got a couple of problems. Number one, I can't take the derivative of this function because it has 2 variables in it. So I'm going to need to work this formula down to just 1 variable. And then I'm not really given an interval. So in these applied optimization problems, we are going to have to think about what a reasonable interval would be. So let's talk about how to get this formula down to 1 variable. You're going to do this with your constraint, and that's the 2,400 feet of fencing. So let's think about an equation that involves that 2,400 feet of fencing. So we've got 2,400, and that's going to be what we're going to use to build the 3 sides of our rectangular pen. So I've got to build an H, a W, and another H. So this is going to be 2 H's plus 1 W. And what we're going to do is solve that constraint equation for one of the 2 variables. And it really doesn't matter which one. This equation is easier to solve for W, so I'm going to subtract 2H from both sides and get that W is equal to 2,400 minus 2H. And that W is the same W that's in my area formula. So I can take this 2,400 minus 2H, which is equal to W, and replace this W over here with that expression. So I'm going to make my area equation, and start using A instead of the word area. It's H times W, and W is getting replaced with 2,400 minus 2H. And that's going to be my function. Now that it's down in 1 variable, I can take the derivative. I'm going to go ahead and distribute that H to make it a little more derivative friendly. And I'm even going to call this A of H, now that this is a function of just the height of my pen. So that's going to be 2,400H minus 2H squared. All right, so we're going to find the absolute maximum of this function, the absolute maximum area, but we need to have an interval. In your 4.3 homework, I would give you that interval. Here, we're going to have to figure out what that interval might be. So we're going to make an interval, and there's really more than one correct answer here. It's going to be an interval for h values, and we're going to try to pick some ridiculous extreme values where it's obvious that our answer lies between those two values. So what's the most ridiculously small value I could pick for h, the height of my rectangular pen? I'm going to say 0. How about 0 feet? That would be the dumbest pen ever, right? We would make it have no height. So we take all 24 feet of fencing and lay it right up against the river. Couldn't even fit our goat in there, but it is a ridiculous sort of low bound on the value of h. And what would be the high bound on the value of h? Well, got 2,400 feet of fencing. I could use all 2,400 on the height of the pen. That would be like 1,200 on this side and 1,200 on this side. So I'm going to say that 1,200 is a good max spot. And like you could have done like 1 feet and like 1,100 feet, something that's obviously very ridiculous, something like that. But 0 to 1,200 will work. All right, so let's find the derivative of a of h. We're going to take a prime of h. Derivative of 2,400h will just be the coefficient, 2,400. And then derivative of 2h squared is going to be 4h, so minus 4h. And we're going to find the critical points. So where it's equal to 0, this one will never be undefined. So we're just going to set it equal to 0. Let's add 4h to both sides. And I get 2,400 equals 4h. Divide both sides by 4. And we get that h is equal to 600. So just like in section 4.3, we're going to test our critical point and both of our endpoints. So we're going to find a of 0. That's our first endpoint. We're going to find a of 600 and a of 1,200. And we're just going to make sure that we have found the absolute maximum possible area, that we haven't accidentally found the absolute minimum possible area, something like that. All right, so I'm going to go to my area function. So just as a reminder, that's over here in the blue box. And we're going to plug in to those three numbers. All right, so I'm going to find a of 0, so 2,400 times 0 minus 2 times 0 squared. That's a bunch of 0. That makes sense. Remember, that was the pen where we would make the height 0, so we used all 2,400 feet of fencing on the width. There's no area in there because there's no height to it. Let's see, 600. We're going to do 2,400 times 600 minus 2 times 600 squared. And we're going to let the calculator tell us what that is. All right, so 2,400 times 600 minus 2 times 600 squared gives me 720,000. And 720,000 kind of jives with what we were seeing on that Desmos page. We saw a little bit over 700,000 square feet of area was going to be our maximum possible area with our goat. And then we're just going to double check this a of 1,200. This one is also going to end up being 0. Plug this in and you can check on your calculator that it is, because that was the pen where we made 1,200 feet on this side, 1,200 feet on this side, and didn't have any left over to make any width. So that was the one that had 0 area to it as well. So when we started this whole problem, I asked what is the maximum possible area of our goat pen? And the answer is that 720,000. So 720,000. And we want to put units on that. Distances in this problem were measured in feet. So area is going to be in square feet. So 720,000 square feet. And we'll just mention that this happens when h is equal to 600. Just to give a little bit of a clue to anybody who actually wants to go out and build a goat pen.